Hi everyone. Notes 3.7 are on connecting everything together with direct and partial variation. And we're going to do something called the rule of four. And the rule of four is just pretty much saying that a mathematical relation can be represented in four different ways. We can represent our relation in words, in a chart, and this is numerical, in a graph, and obviously that's graphical, or in an equation. And this is an algebraic representation. So if you take a look at our first scenario, it tells us the information in words. So we know this situation in words, and it's telling us that a cable car starts at a height of 200 meters and is descending at a rate of 10 meters per minute. That it starts at a height of 200 meters and that it's descending at a rate of 10 meters per minute. So all of this is some really important information. So before we do anything else, I want to identify what are our variables. We have two different variables. We have our height in meters and our time in minutes. And the height depends on how much time has gone by, which means the height is the dependent variable, which is the y. And we'll call it h. So we'll say h for height, and the other variable is time. And since height is dependent, that means time is independent, and that is the x. Okay, so that's going to help us out with our table. So we're going to say time right here in minutes. And on this side, we can say height, and the height is measured in meters. And we know that in 0 minutes, the height will be 200 meters. Okay, it tells us that it starts at a height of 200 right here. So this, we know that our initial value is equal to 200. And then every minute it goes down by 10 meters. So we know that after 1 minute, it went down by 10 meters. So now it's at 190 meters. At 2 minutes, it's at 180 meters. 3 minutes, it's at 170 meters, so on and so forth. But in my chart here, it's not really showing me a whole lot. So instead, what I want to do is I want to maybe skip some values, okay? And we can still have this work out for us. So this chart is totally fine, this one that we have here. So I'll just put it in the corner here. But I'm going to get rid of the remaining 3 values here. And instead, maybe I'll go by 5s and see what happens if I go by 5s. So if it's going down at a rate of 10 meters per minute, then we know that in 5 minutes, it's going to go down by 50 meters because 10 meters per minute, multiply each one by 5. 1 minute is 10 meters, so 5 minutes is 50 meters. This is where these equivalent ratios are really helpful. But it's going down, so we're going to have negative 50. So this should be 150 because 200 minus 50 is 150. After 10 minutes, another 5 minutes have passed, so it would go down by another 50. So this would be 100. And then after another 10 minutes, we would be down another 50. So this would be at 50. Another 5 minutes right here. So see how we're being consistent here. We would be at 0. So now we know when the cable car will reach the ground. Okay. All right. So that is our table. Now we can use our table or our words to do our graph. So first thing on our graph though is we have to label. So we know that the time is going to go on our x-axis and the time is in minutes. And we know that the height is going to go on our y-axis and that the height is in meters. And then here we have 0 minutes. And I want to go to 20 minutes just to see what's going on. So to figure out how to space this out, I know I want to go out to 20 right here. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots, which is nice and convenient because if I want to cover 20 minutes in 10 spots, that means I can do 2 minutes per spot. So I can say this is 2, 4, 6, 8, 10 minutes. I don't have to label every single one, 12, 14, 16, 18, 20 minutes. If you want to, you can, but I don't like to label everyone because it gets really crowded and because it takes a lot of time. Okay, and then we know that our maximum height is going to be 200 because it starts at 200 and then it goes down. So we know it's not going to go above 200. Same thing, we have 10 spots right here. We want to cover 200 meters in those 10 spots. So when I divide that, I get 20. So this is 20, 40, 60, 80, 100, and then 20, 120, 140, 160, 180, 200. Sometimes it's not going to be nice, even, pretty numbers, and you just choose numbers that are close to the numbers that you got when you divided, and we'll talk about that more in class, okay? So we know that it starts at a height of 200 meters. So we're going to have this start at 200, and we know that it's going down by 10 meters every minute. But we can also use this chart right here. So we know that at 5 minutes, so 2, 4, 5 is right here, 5 minutes, it will be at 150. We know that at 10 minutes, it'll be at 100. We know that at 15 minutes, it will be at 50, and that at 20 minutes, it'll be at 0. All of that information I got from my chart right here. So here we can say that my graph will end up looking like this right here, okay? And that's all we have to do for our graph. And in our equation, we have h as our height right here. We know that our height is equal to, it starts at 200. It tells us it starts at 200, and it goes down by 10 meters for every minute. Or we could say it's going down by 10 meters for every minute, but it starts at 200. And just a quick note, whenever we're trying to find our equation, we need two things. We need our rate of change, which is this -10 that we have here, and we need our initial value, which is this 20 that we have here. Okay, so now we've got scenario number 2. This time we're given our information in a table. So we know that our independent variable is the time and that our dependent variable is the cost. So we know that the cost of something, and we don't have that much information here, is dependent on the time. We can kind of make up what's going on here. So let's go ahead and do our graph first. So here I'm going to label time right here, and time is measured in hours. And here we're going to label our cost, and our cost is measured in dollars, and we're going to start at 0, and I'm just going to go up by ones, 1, 2, 3, 4, 5, because my chart is going up by ones here. And then here we know that our initial cost right here, our initial value is going to be $40, and we see here that it's going up by 15 every single time. The time goes up by 1 hour, right? So we've got our rise over here. We've got our run over here, okay? So let's go ahead and see how we want to space this out right here. So we know that this initial cost is $40, and we know that at 1 hour, it's going to be $55. So 1 hour, I'll go from 1 hour here to $55, which is approximately here. We know that 2 hours is going to be $70. So we'll go from 2 to 70, and then I have a point right here. We know that 3 hours is going to be 85. So we'll put our point right here, and then we can just draw our line in right here. And because it's going to continue to go on, we'll put an arrow right here. Okay, so now let's do our equation. I'm purposely doing the words at the end because we can make up any scenario that we want as long as it goes along with this. But let's go ahead and do our equation. So we have our time, we'll call T, and then we'll call C our cost. And so it tells us here that our cost is starting at $40. It tells us in the table and the graph that it's starting at $40 and that it is going up by $15 for every 1 hour. So right here, let's find our rate of change. It's $15. We know it's up 15 for every one. So $15 for every 1 hour is $15 per hour. We could also, if you wanted to, just see that this right here is going up by 45, and this right here is going up by 3, and if I do 45 over 3, I still get 15. You have a lot of options for what to do for that. We can even use our graph. We could say, oh, here's our rise, here's our run. It went from 50 to 80 right here. So it went up by $30 because 80 minus 50 is 30. And then it went over by, it went from 0 right here all the way to 2 right here. So it went over by 2 hours. So $30 in 2 hours is still $15 per hour. So you've got a lot of different ways that we can find our rate of change. Regardless, our rate of change is 15. So we can say this is $15 for every hour, which we called T is time. So we called it T. If you prefer, you can change this to an H and put an H here. It doesn't matter. If the variables are not defined for you, you can choose whatever letters you like. You also have the option to say the cost is $15 per hour plus an additional $40. And just a reminder that the two things that we need whenever we're trying to find an equation are the rate of change, which we figured out here was 15, as well as the initial value, which here we know is this $40 that we have right here. So now we want to put this in words, and you can make up any scenario you want. The more creative you are, the better. So for example, right here, we could say, to raise money, your school is having a game night. It costs $40 to get in, so this is important right here, and you have to pay an additional $15 per hour. So just a quick note that this is your rate of change and that this $40 is your initial value. And all of that information. All right, so let's take a look at scenario 3. This time we're given our information in a graph right here. So we know that the time right here is the independent variable and that the distance in kilometers is the dependent variable. And so here we'll call this T and we'll call this right here D, okay? And let's go ahead and fill in that information in our table. By the way, you can do all of this work in any order you want. It's totally up to you, okay? Whatever you feel most comfortable with. I like doing a table because I like to see the numbers in front of me. I feel like that helps me. But if you don't want to do that first, you don't have to. So we've got time in hours and we've got distance in kilometers, okay? So here I'm going to say after 0 hours, I went 0 kilometers, and that 0 is your initial value. This is really important right here. So this is your initial value. After 1 hour, we don't know exactly how far we went, so I'm not going to include that in my chart, but I do know that after 2 hours, we went 10 kilometers. 3, I can't tell exactly, but 4, I can for sure tell. 4 hours was 20 kilometers. 5, I can't tell exactly, but 6 hours I can see was 30 kilometers. And I can see the pattern, right? I could keep going if I wanted to. I could say that 8 is 40 because each one of these is going up by 2s and each one of these is going up by 10s. So if you look here, we can see, yep, for sure, 8 does definitely correspond with 40. Now I want to write my equation, and there are two things that I need when I write my equation. I need the rate of change and I need the initial value. So the rate of change is found several different ways. We can see here that this is going up by 10 kilometers for every 2 hours. So for that rate of change, we could do 10 kilometers in 2 hours. So we can say that this is 5 kilometers per hour. So a rate of change is 5 kilometers per hour right here. We can also do rise over run. So for example here, and use these 2 points as my starting and ending points. I can see, oh, it went up this much and it went over this much. Well, it went up from 10 to 30, so this rise is 20 kilometers, okay? And then it went over from 2 to 6, so this run is 4 hours, and 20 divided by 4 is still equal to 5, so we still get that 5 kilometers per hour. Here, our initial value we know is 0. So we can say a couple of options right here. We can say that our distance is equal to 5 kilometers for every hour. And we don't have to put anything else down because the initial value is 0. So we don't have to include that 0. Or we could say our distance is equal to, we started right at the beginning, we hadn't gone anywhere at all, plus an additional 5 kilometers per hour. Or we could say 5 kilometers per hour, plus we started right at 0. But this is typically how you will see it. Okay, so now for our words, we can just say, Carl left his home and walks at a rate of 5 kilometers per hour. So this right here, the fact that he left his home is telling us that our initial value is equal to 0. And the fact that he's walking at a rate of 5 kilometers per hour right here is telling us that our rate of change is 5. Okay. All right, in our last example, we're given our equation, which is C equals 15m plus 80. So a quick note that this right here is going to be your dependent variable, and this one right here is going to be your independent variable. And we know that because the equation is literally saying that the cost is equal to 15 times the m, which is the independent variable, plus 80. So this is literally saying, our equation is literally saying that the cost is dependent on the whatever m is multiplied by 15 plus 80. Okay, so based on that, we can say right here that our cost, and sorry, I'm using C for cost, but C could represent anything that would make sense in this context. So I'm going to use the word cost. So our cost right here, we'll use dollars since we're in Canada, is going to be our dependent. And then our M right here, let's say M stands for months, just because that seems to make sense. So this is our time in months is our independent variable. Awesome. So now our rate of change, according to our equation, is equal to this 15. How do I know that's our rate of change? Because this says 15 for every M. And anytime we hear for every anything at all, this is your rate of change. So we'll say this is $15 for every month. All right. And then our initial value is going to be equal to whatever is added on here. So this is going to be $80. So this is our initial value. So here we know that for 0 months, we're going to be paying $80. And then this is saying it's going up by $15 for every month. So we know after 1 month, it's an additional $15. So it's $95. After 2 months, it's an additional $15. So add 15 right here, and we can see that we're going to get $110. After another month, it's going to be an additional $15 after that. So it'll be $125, so on and so forth. Here, to do our graph, we have our time here in months. We have our cost here in dollars. So when I do my graph, I know that the initial cost will be $80. So right here, this is the initial cost. After 1 month, we'll be at $95. 95 right here. After 2 months, it'll be 110. After 3 months, it'll be 125. Okay, so looking at this here, this is what my graph is going to look like right here. And then lastly, we need to talk about what's happening in words. So we know right here that our initial value is $80. How do we know? From our equation, from our table, and from our graph. And we also know that the rate of change is $15. How do we know? From our equation, from our table, and then this went up by $15 for every 1 month. So from our graph as well. So we need to have some type of a situation that starts at $80 and goes up by $15 per month. So we can say, for example, Jaya joined a gym. It cost $80 to join and an additional $15 per month. So this right here is our initial value. And this right here is our rate of change. Last thing I just want to talk about in respect to all of these examples is whether or not these are direct or partial variations. So just a reminder that the initial value for direct is 0. The initial value for partial is anything other than 0. So in scenario number 1, we know that our starting point, our initial value, is 200. It tells us this in the table here. It tells us in the description here. It tells us in the graph here. And it tells us in the equation here. So because we know the initial value is 200, we know that this is an example of partial variation because it does not start at 0. In our next example, so this tells us here that the initial value is $40. We know it starts at 40 in our table right here. We know that it starts at 40 in our graph right here. And from our equation, we also know that it starts at 40 from these values right here. So because it's not starting at 0, the initial value is not 0. It is another example of partial variation. In scenario number 3, we know that the initial value from our description is 0. In our table, it tells us the initial value is 0. In our graph, it tells us that the initial value is 0. And in our equation, it tells us that the initial value is 0. And just a little reminder right here, the fact that there's nothing here also tells us that the initial value is 0. And since the initial value is 0, this is an example of direct variation. And then in our last scenario that we have here, our initial value in our description, it tells us it's 80. In our chart, it is also 80. In our graph, it is also 80. And in our equation, it is also 80. So this tells us this is an example of partial variation. And that's it for this video. So if you have any questions, let me know. Other than that, I will see you in class. Have a good one. Bye.